Well, hello ladies and gentlemen, welcome to lesson 3 on trigonometric identities. Today we're going to talk about the sum and difference identities, dealing with the idea that you have two angles within the same trigonometric function. What do we do? If you take a look at the top of our lesson here, we have all the identities that you're going to have to be dealing with. Now, the question always comes up, well, how do I know which one to use in which situation? Well, obviously you'll notice that inside the function you either have a plus or a minus. And that's certainly one way to tell which one you're going to use. The second way, the way I find most useful, is take a look at whether they have a cosine times a cosine and a sine times a sine, or if it's a sine times a cos and a cos times a sine. If you see that the identity that you're trying to plug in for has a sine times a cos, then chances are you're going to be using the sine double angle identity versus the cosine double angle identity. That's enough talking about it. Let's just get right to it. First, let's take a look at this idea of the cosine of pi plus 2a. Well, again, this is simply a plug and chug kind of thing. We notice again that it's a plus. We notice again that it's a cosine. So we're going to use the identity that says the cosine of pi plus 2a is equal to the cosine of pi times the cosine of 2a, subtract the sine of pi times the sine of 2a. You'll notice again that I have deemed this to be our a and this to be our b. Keep in mind, please, that the variables may not match what's inside the brackets, but we definitely have to go according to the convention that's established by the identity. So, we have this. Now we can simplify some things a lot. If you remember back when we dealt with the graphing of trigonometric identities, or if you just know how to plug things into your calculator. You might notice that the sine of pi, well, what is the sine at pi? If you remember our graph, it looks something like this, and that was pi. So the sine of pi is actually 0. If you think about the cosine now, we again can look at the idea that it started at 1, came across, leveled off, and back up, which means the cosine of pi is actually equal to -1. So, in putting these values in, we can actually simplify this to the negative cosine of 2a subtract 0. So it's just the negative cosine of 2a. So keep in mind that, of course, because we don't know what a is, that we have to leave it in its form like this. So why don't you give b a try and see what you get. Okay, so hopefully we had a look at b, and now we can do that very quickly. Again, because it's the sine of two angles subtract each other, we call this a, we call this b, and away we go. This is actually equal to the sine of 3 pi over 2 times the cosine of x. Remember, we don't know what x is, so we just leave it as is. Subtract the cosine of 3 pi over 2 times the sine of x. Well, again, exploiting the fact that we know something about the exactness of these equations, we should know that the sine of 3 pi over 2 is -1. Remember, you could just plug this into your calculator and get these values no problem, or know something about the geometry of the system. Cosine of 3 pi over 2, well, wouldn't you know it, that's just equal to 0. So we can rewrite this again as negative cosine of x, and that's as simplified as we can get because we don't know anything else. So, again, knowing your basic functions, sine and cosine, is going to go a long way in helping you out. And knowing the exactness equations that we learned from chapter 4. Alright, let's take a look now, and now we're going to go backwards, and we're actually going to simplify this identity in terms of whatever we're given. So, first thing you have to do is identify a couple things. Number one, we identify that this is a plus. That means we're already narrowed down to two identities, either the sine of a plus b or the cosine of a subtract b, to identify which one specifically we're going to use. Again, notice that we have cosine times cosine and sine times sine, so we know that inevitably we are going to use the cosine of a minus b. Now the question is, what is a and what is b? Well, if you take a look at your standard function and you take a look at the function that we're given here, we should notice that this sure looks like a and this sure looks like b, which means that this just becomes the cosine of 2x subtract x. Now, because these are the same variables, we can actually perform the math and come up with a simplified version again of cosine of x. And that, my friends, is as simple as we can get. So again, identify the sign, identify which trigonometric function we're going to use, which identity specifically we're going to use, and then just go ahead and solve. Now, let's go a little more exact yet again and deal with these questions now that have values associated with them. Pi over 3, pi over 6, and pi over 12, 11 pi over 12. Well, these should start ringing in our heads, this whole idea, and I know I mentioned this previously and now they're back in full form, the idea of the 30, 60, 90 triangle, or in this case, pi over 6, pi over 3, and of course pi over 2. Well, we remember that the ratios were 1 to 2 to root 3, meaning that, for example, the sine of pi over 6 is opposite over hypotenuse, which is 1 over 2. The other triangle we definitely need to remember is our 45, 45, 90 triangle, or the idea of pi over 4, and 90, or sorry, pi over 2. And again, we should know that this is the ratio of the sides. So again, cosine of pi over 4 is 1 over root 2. Well, how does this apply to stuff? Well, in a couple of awesome different ways. If we take a look, first we need to know which identity to use. Well, lucky for us, it's the same that we just used previously, and that's equal to the cosine of, call that a, that b, pi over 3 subtract pi over 6. Keep it exact instead of taking it to decimal, because what you're going to find out is that this is actually equal to the cosine of pi over 6. Well, you could leave it there, but this time we actually have an identity inside that we know what the answer is, because if you take a look back here at our triangle, the cosine of pi over 6 is adjacent over hypotenuse. Well, that's just equal to root 3 over 2. And that, my friends, is your final solution to this question. I challenge you to put this into your calculator and verify that this is true. But definitely, if you've gone the right way from start to finish, at the end you should be able to give me in exact terms what the cosine of pi over 6 is. Now that I've done part A, let's go ahead and do part B by yourself. Okay, so hopefully we had a chance to look at part B. Let's take a look at what we ended up with. Well, we know again that this is A and that's B. So when we have sine, cos, and we have subtract in between, which means this should be equal to the sine of 11 pi over 12 subtract pi over 12. Well, let's just do the math, and we end up with the sine of 10 pi over 12, and that can be reduced to the sine of 5 pi over 6. Okay, so flashback into the past. When we were dealing with the coordinate system, which was 0 and pi over 2 and pi and 3 pi over 2 and 2 pi, we were learning that 5 pi over 6 is smack dab in here somewhere, and that the reference angle here was actually pi over 6. And if we wanted to rewrite this in terms of the reference angle, we knew that because it was using the cast system and that cosine was the only positive down here, to rewrite this in terms of the reference angle, we would have to rewrite this as the negative sine of pi over 6. Because keep in mind, we can't be exact with 5 pi over 6, but we sure as heck can be exact with pi over 6. So The negative sign is important, again, because it's in quadrant 4. And pi over 6 is because that is, in fact, the reference angle. Which means now we can just, and I'll just kind of skirt around here, rewrite this exactly as negative 1 over 2. And again, I got that because up at our triangle, again, the sign of pi over 6 is opposite over hypotenuse, which is 1 over 2. We have to remember the negative sign. So if you got that, great. If not, maybe pause, go back, take a look again. Really make sure you understand this. I know in chapter 4 we definitely had some problems with this idea of exactness. Okay? All right, well, let's move along to some more exact stuff. Now this stuff can get a little bit tricky because we have to actually play around with the numbers a bit. Now, my immediate thing I will say is it's definitely worth thinking in degrees. I know, did I say it? I totally said it. I said we'd never go back to degrees, but honestly, when we're thinking about the 45, 45, 90 triangle and the 30, 60, 90 triangle, and we're thinking about this idea of exactness, sometimes the radian measures don't exactly give us the full picture of what we're dealing with. So at this time, I would say, you know what, go ahead and think about it in terms of degrees, and I'll explain why. We want to find the exact value of the cosine of pi over 12. Now we know that we don't have any exact term for pi over 12 right away, but we should know that pi over 12 is equal to 15 degrees. Now again, I just did that calculation using 180 divided by pi. That gives you 15 degrees. And then the question becomes, and this is me thinking now, 30, 60, 90 triangle and the 45, 45, 90 triangle. How can I rewrite angle in terms of these? This is what I'm thinking the whole time, because watch, I can get 15 degrees if I do 45 degrees subtract 30 degrees, and that's going to be equal to 15 degrees. So I can rewrite now the cosine of pi over 12 as the cosine of, now again we know 45 degrees is pi over 4, and we know that 30 degrees is pi over 6. Now you see what we're getting at? This is the double angle identity that we've been talking about previously. Now in this case, we have this, but we can rewrite it in terms of the right side of its identity, which says the cosine of pi over 4 times the cosine of pi over 6 plus the sine of pi over 4 times the sine of pi over 6. And now we can get some exact values. We know again from our triangle that the cosine of pi over 4 is 1 over root 2. The cosine of pi over 6 is root 3 over 2. Plus, again, the sine of pi over 4 is 1 over root 2. And the sine of pi over 6 is 1/2. And that's just equal to, and I'll do an arrow, I know this is a math faux pas, but whatever, we're here now. This is in fact equal to the square root of 3 plus 1 divided by 2 root 2. So I kind of sped ahead on the simplification, but obviously if you take a look at the bottom, we've got a 2 root 2, and then you're just left with this root 3 plus 1 times 1, which is 1. So I end up with this, which is an exact value, and wouldn't you know it, if you plug in cosine of pi over 12 in your calculator and then plug in the square root of 3 plus 1, all of that divided by 2 root 2, you will end up with the same decimal. So hallelujah, we know we're correct. Now that I've done my part, you do yours and do part B. Alright, so part B is very much like part A, except in this case, we know that 17, I'm going to draw a line here just so we know, that 17 over 12 pi is equal to 255 degrees. Again, I know I preach against it, but hey, this time degrees actually makes a little more sense. And we know that 255 degrees is equal to 210 degrees plus 45 degrees. Well, again, we can't be 100% exact with that because we don't know what 210 is, but we can rewrite 210 as 180 plus 30 degrees. Well, that tells us a couple things. That tells us that this is definitely going to be in quadrant 3, 210, duh. And we know that now, when we do exactness, we're going to be dealing with the reference angle, which means there's going to be potentially a negative sign. So, all that being said, we can rewrite this as the sine of. Now, we're going to end up with 210 degrees, which is 7 pi over 6, plus we have 45 degrees, which is pi over 4. Now again, I'm using the definition that 180 degrees is equal to pi radians, and that's our conversion rate. So we can then rewrite this as the sine of 7 pi over 6 times the cosine of pi over 4 plus the cosine of 7 pi over 6, run out of room, times the sine of pi over 4. Alright, cool. So this is where this whole reference angle mumbo jumbo comes in, because now we can say the sine of 7 pi over 6, well, the sine of pi over 6 is 1/2, but because it's in the third quadrant, it's based on the reference angle, it's negative in the third quadrant. This ends up being negative 1/2. I challenge you to go look at chapter 4 again if this doesn't make sense. Times the square root of 1 over 2, that's the cosine of pi over 4, plus, this one's again a bit trickier, the cosine of 7 pi over 6 is negative root 3 over 2, and the sine of pi over 4 is 1 over root 2. So, sorry for the messiness, there's a whole lot going on there, but when you reduce this, you end up with, this is kind of cool, I factor out a negative sign and I end up with the square root of 3 plus 1 divided by 2 root 2. So again, if you got this, fantastic. If not, go take a look at A again, see if you missed something on the first instruction, and then come back and try this again. But the whole idea comes from this idea of cast up here. So this, I'm going to put a big fancy star right in the middle. Really important you go back and take a look at that, because exactness won't do anything if you can't get those right. Okay? Alright, so for part C, I'm going to work through the first little bit for you, and then let's see if you can finish it off. So, I know that C is the secant of 5 pi over 12. Well, even before we go, we can rewrite this as 1 over the cosine of 5 pi over 12. Well, that's cool. Well, what do we do with that? Well, on the side, we know that 5 pi over 12 is equal to 75 degrees. And that should immediately tell you that, well, wait a second, that's the sum of 45 degrees plus 30 degrees. Wicked. What are we going to do with that? Well, we're going to rewrite this as a double angle then, and put 1 over the cosine of pi over 4 plus pi over 6. Okay, nice. Now, take a minute, see if you can finish off from here. Okay, so hopefully you finished off from here, because now we just plug in for 1 over the cosine of pi over 4 plus pi over 6, and put in 1 over, it's going to get ugly, the cosine of pi over 4 times the cosine of pi over 6, subtract the sine of pi over 4 times the sine of pi over 6. Sweet. Okay. And again, going back to this idea of reference angles and all that jazz, because this is 75 degrees, we know that this is in quadrant 1, which means that our principal angle is our reference angle, so we don't have to do anything with that, which means we can just plug in 1 over. And here we go. This is 1 over the square root of 2. This is root 3 over 2. Boy, this looks familiar. Subtract 1 over the square root of 2 times 1/2. And now I'll go up here just so I don't commit another math foul. And that's just equal to, after a little reduction and simplification, 2 root 2 over the square root of 3 minus 1. So again, The bottom down here got a common denominator. The denominator in a fraction in the denominator pops up to the numerator, and we end up with something like this, which is all nice and pretty. So again, I say, if you're not 100% sure if what you get is the correct answer, plug in secant of 5 pi over 12 in your calculator, then plug in your exact value form and see if you get identically the same decimal. If you don't, then you've definitely made a mistake somewhere. Okay, so we're almost done with this lesson. We just have to talk a bit now the idea of proving with these identities. So we have this idea that says the cosine of pi over 2 plus theta equals negative sine of theta. Ideally, what you're thinking right away is, okay, this is a double angle. I'm going to have to input the double angle identity. Chances are something's going to cancel or change into 1 or change into something exact that I can deal with. As I've done previously, all proofs, I like to deal with just the left side. And we go a little something like this. Well, cosine of pi over 2 plus theta, we know from our identity, is equal to the cosine of pi over 2 times the cosine of theta, subtract the sine of pi over 2, oh, I'm going to bleed over, times the sine of theta. Fail. Well, we take a look, cosine of pi over 2, oh nice, that's just equal to nothing. Woo! And the sine of pi over 2, well, that's thankfully equal to 1, which means this cancels, and all we're left with is the negative sine of theta. Well, wouldn't you know it, that's what we were looking for. Left equals right, and QED, baby, there we go. All right, give B a try. Well, B was just as easy as the first one was. If we take a look, the sine of pi minus theta equals the sine of theta. Let's put that pretty line down there. We can input the double angle identity, the sine of pi times the cosine of theta, subtract the cosine of pi, man, I'm bleeding over again, times the sine of theta. Alright, well, the sine of pi equals nothing. Again, think of that equation, think about that graph, and you should have no problem coming up with that. And the cosine of pi, well, that's cool, because that's equal to negative 1. Remember, that's the minimum on the first period. And so what happens? This cancels out to nothing. We have a subtract a negative sine theta, which is just equal to sine theta. Left equals right. QED once more. Beautiful. Again, these identities, sometimes they're as simple as they look. Okay? All right. Well, let's get to the final question of the day, and then we're out of here. Oh, final 2 parts of the question. And the question goes a little something like this. Given that cosine of A equals 3/5 and cosine of B equals 5/13, when 0 is less than or equal to A, which is less than or equal to pi over 2, and 3 pi, blah, 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 blah. What does all this mean? Well, what does that mean? This means it's quadrant 1, and this means it's quadrant 3. Uh-oh, chapter 4 is coming back to haunt us again. Well, I would say before we deal with anything else, let's get a wrap on exactly what this geometry looks like. So let's draw our coordinate axes over here. When we take a look at the cosine of B equals 5 over 13, and the cosine of A equals 3 over 5, it tells us that A is in the first quadrant, so that's that bad boy right there. How do we get that? Well, cosine is adjacent over hypotenuse, which means if we were to draw it like so, adjacent is 3 and the hypotenuse is 5. And this here is angle A, which means if we want to find the sine of A, we need to know what that side is there. Well, lucky for us, we know the Pythagorean theorem, and that's going to be equal to 4. The same way, and I'll draw a different color to be cool, the cosine of B is 5 over 13, but we know that that is in quadrant, oh, I said 3, I totally meant 4, that this angle is in quadrant 4, and how do we get that? Well, again, it's adjacent, so it's still 5 over hypotenuse, but because it's in quadrant 4, down here, it looks something like this, where again, this is a right angle triangle, this is 5, and this is 13, which means again, if we use our Pythagorean theorem, we get an answer of 12. But because it is in the fourth quadrant, This is a negative 12. That's why it dipped down. That's why it's important that we know this stuff up here and not screw up that it's a 4 instead of 3. So, what does this all mean in the end? Well, what this means is now, when we input, well, the cosine of A plus B is actually equal to the cosine of A times the cosine of B. Subtract the sine of A times the sine of B. Uh-oh, look, we need to know what the sine of A and B is. So, come back up here. The sine of A equals opposite over hypotenuse, which is equal to 4/5. And over here, the sine of B is equal to opposite over hypotenuse, which is negative 12 over 13. Notice that negative. That's going to be crucial. Cool. Let's plug it in. The cosine of A, we already said, is 3/5. Cosine of B, again, we said is 5/13. And we're subtracting the sine of A. Yay, we found that. And the sine of B, well, that's negative 12 over 13. Sweet. We can reduce this in fractions, but we end up with something like this, 63 over 65. Remember, our common denominator in this case is going to be 13 times 5, which is 65. And then we have 15 on top, subtract a negative 48, which means plus 48, and we end up with 63 over 65. That's it, sports fans. That's our answer to part A. Let's give B a try right now. Alright, folks, well, let's take a look at this solution. We see that we have the sine of B minus A. Now, I'll just do a quick rant about the idea that these letters here may not match general equation. So you'll notice that we're using A's and B's, but in this case, when we plug in for our general equation, which labels this as A and that as B, that we're going to have to do a flip-flop. Now, please keep in mind that these are two different A's and B's, and you just have to plug in according to how you know how to plug these in. So in this case, we're going to end up with the sine of B times the cosine of A, subtract the cosine of B times the sine of A. Okay? So again, in our general equation, this here would have actually been A, and this here is B, and it is that case, except for in this case, our A is B, our B is A. Our brains are just going crazy on this. Please try your best to get this all straight in your head. But regardless of how you do that, you know that the sine of B, well, we did this already. That's negative 12 over 13. Sweet. And the cosine of A, well, we were given that. That's 3/5. Subtract the cosine of B, which is 5/13, and the sine of A, which is 4/5. So again, we have our common denominator of 65, but in this case we have negative 36. Subtract another 20, which means we're going to end up with negative 56 over 65. Boom.